Okay, let's begin. We may have a few latecomers join us here in the next few minutes, but we can certainly begin. Today's speaker is Mr. Jim White, who is the Director of the Measurement Science Section in the Instrumentation Controls Division of the Oak Ridge National Laboratory. Jim is a two-time graduate of this department. He got his BS in 67, and he got his master's in 68, and then he did everything else for the PhD except the dissertation project, and so he never finished his dissertation. He's been at the Oak Ridge National Laboratory for the past 33 years. He was in the reactor division for the first few years, and then it became the Engineering Technology Division. And then, for the most part of his career, he's been in the Instrumentation and Controls Division. Today, his presentation is entitled Overview of R&D Activities in the I&C Division of the Oak Ridge National Laboratory, which includes opportunities for research collaboration. Jim, welcome.
Thank you, Lee. And thank you for inviting me here to give you this talk. I feel like I've come home. I've been in this room before, in a lot of these classrooms. All the professors look a lot different now than they did when I was a student. A little friendlier and not as intimidating, and a little older, but not much. My goal in this presentation is to give you an overview of a lot of the research and development in our division that I think is pretty exciting. That's what has kept me at the lab for 33 years. I never intended to stay there that long. And I hope to share some of that enthusiasm with you and tell you the areas where we're looking for some collaboration, some help. And maybe some of you would like to contact me at this email address later to discuss further these opportunities for collaboration. We maintain truly leading-edge capabilities in instrumentation and controls in the division. I'm going to explain this to you in just a second. We have 132 research staff and 104 technical support and management system staff, which manage about 80,000 instruments at the laboratory, keeping track of their calibration to NIST standards. The research staff do everything from putting a little chip on a bee to track bees, to helping the Navy track their new submarines. The Navy finally generated submarines that were quieter than the ability we had to measure them, and so they came to the laboratory to see if we could develop a more sensitive way of characterizing our submarines, and we did that. We put together a bunch of hydrophones, thousands of them, and we suspend them in the ocean just like this at some depth. The submarine runs between all these things, and we characterize the noise emanations from the submarine. So that we put together, to do this, the world's largest computing resource at one time. It had that distinction for about 3 weeks. You don't have the largest computing resource in the world for long. And that resource is still on the U.S. Hays, and some of our staff are still going to the Bahamas to do those measurements. Tough duty. This is a command and control vehicle in Europe that we were asked to instrument and help them be able to communicate with other command and control vehicles. And this is an integrated chip that I'll talk to you about later. And if you were sitting in front of a screen, you see a little mouse here that is injected into this system where we do computer-assisted tomography. I'll talk about that a little bit more in the future. I'm going to show you this organization structure first to show you where I am. I'm head of the measurement science. I report to Dan McDonald, the division director. Bob Uhrig is our distinguished scientist. Our chief scientist has retired, in case any of you would like to apply for the position. And we have John Mahauso, who's corporate fellow, and we have a program development office. I'm going to refer to this again when I describe a new control theory approach that we developed a few years ago. So we may come back to that. Our core business functions are shown on the next two slides. The electronic systems, that's one of the sections. deals in RF and microwave design, some of the world's leaders in that. We do custom chips that I'll talk about a little later on in very high-performance systems. In measurement science, we do advanced nuclear measurements and controls. We have a lot of nuclear engineers in my section. We do general sensors and instrument research, and then one of our real growing areas right now is advanced laser and optical technologies. The third section is signal information and knowledge processing, and these guys are really phenomenal. I'll talk about some of their work today. But they do high-performance real-time data systems, image science, machine vision, advanced signal information and knowledge processing methodologies, and then they also support the experimental and operational facilities on the reservation. I&C is a research division, but we have about 19 others, and almost all of them use us to some degree or another. In terms of our educational background, you see that, or hopefully you can see, 64% of us have electrical engineering degrees, about 20% have nuclear engineering degrees, computer science is only 2%, physicists are either 5 or 7. I can't tell the difference on this slide, but that gives you a general idea about our educational backgrounds. We serve 7 market areas, and this is a busy slide, but it's important because I want to explain to you the breadth of the work and the breadth of the research opportunities at our facility. A new area for us is instrumentation for bioscience and bioengineering. That's a really growing area. We think that physical science is making way and is going to be a little bit in the shadow of biological science in the future. So we're trying to figure out how to do measurements and controls in biological and very small systems. Our biggest markets right now have to do with threat reduction in force and infrastructure protection. This is protecting us against terrorist threats, doing treaty verification, and protecting our armed forces when they are out on the seas or in foreign lands. We have a lot of work for DOE industries of the future. These are the industries that are the most polluting and energy inefficient, like steel, aluminum, glass, chemistry, forest and paper products, and 3 others that I can't remember standing up here in front of you. Some of our really exciting work is in the semiconductor industry. You know, as they try to make these chips about the size of my thumb and put more and more details into those chips so that we get down below the wavelength of light, even being able to characterize those and control the production is becoming a very important economic force in the world. I'd like to give you a figure of merit. It used to be that nuclear power plants cost about $2 billion when they were built on some sort of scale that you could depend on, time scale. A new fabrication facility for semiconductors costs about $4 billion. Could be $6 billion. They're much more complicated than nuclear power plants now. We, of course, do instrumentation for national and international science experimentation and facilities, and then we do general support. So that's a great breadth of opportunity for work. That's why I'm still at the laboratory. I can do just about anything I want to do. There's a lot of opportunities for intellectual stimulation, just like in a university. Our biggest market is the blue one, and that is whatever that is. That's our internal markets. You see these colors aren't showing up very well, I'm sorry, but the security market is our biggest market. I think when you look in the archives, and you can see the colors a little better on the computer. But we had $28 million in funding last year. This year we think we're going to have $32 million in funding. That translates to a growth opportunity, and because of that we're in a hiring mode and looking for collaboration. We do some really great research as evidenced by this slide. There's a magazine called R&D Magazine. Every year since 1963, they have selected the 100 most innovative and important inventions of the year in the U.S. ORNL has won 85 of those. I&C won 16 of the 85. ORNL currently ranks second in the nation. I think we're behind GE. And so we participate in 20% of those, and so we're really big in patents and invention disclosures. As a matter of fact, intellectual property is becoming a force in research in this country that I wasn't aware of 5 years ago. In the last 5 years, it's become very, very important. Our researchers are finding that they can get their own patents and get a revenue stream for them and for our organization, and that's becoming pretty important in terms of a wealth-building opportunity and career-building opportunity. Now I'd like to go through each of the sections pretty quickly. Lee, what's the time that probably everybody will need to leave?
About 2:30.
Okay, great. First I'm going to talk about the electronic systems section. This is the Phoenix experiment at Brookhaven. Here is a man, so you can see how big the experiment is, if that's a human being. The way this experiment works is they get counter-rotating beams of heavy ions, and they have them collide here in this vertex, okay? And what they're trying to look for is fundamental nuclear forces and try to learn more about high-energy physics. We blew this up to here, and I wanted to tell you that we do a lot of the electronics for what they're doing at Phoenix. As a matter of fact, we were responsible for 450,000 channels of electronics to go into this instrument. We finished that this last year. So what we put in there is a lot of custom designed chips. That's a quarter. It shows you about the size of the chip. And we do all kinds of electronics designs that go on the chip. Another part of the collider is shown here, and we've blown that up to show there's a lot of instrumentation that we work on here also. That gives you just some examples of what these designs look like. And here on the outer ring, we have calorimeters to do some energy balances, and we do a lot of custom design for them too. Now, as high-energy physics have gotten, I'm going to backtrack when I hope that doesn't mess you up too much. As high-energy physics experiments have gotten more complicated, we've had to reduce the footprint for the electronics. So we've had to make the electronics smaller and smaller in footprint, and we've had to make them lower power and higher capacity. That has driven a revolution at our laboratory in our ability to do lots of interesting things. One of the interesting things we've been able to do is build intelligent wireless telesensors. On a chip the size of my thumb, right now we have a temperature sensor and an optical sensor, and then 2 open positions for other sensors. We multiplex those and go through an amp and an A to D converter, and then we do something called spread spectrum generation, so that we can improve the ability to send signals in noisy environments and be able to receive them and extract out of the noisy environment the signal we sent. And then we've been able to put an antenna also, an RF transmitter and an antenna, all on something the size of my thumb. Now you can imagine what capability that would give you in trying to go out through the plant and put a sensor on a valve or a pump or some sort of motor, because it can measure various parameters and then send them wirelessly to receivers throughout the plant. So these provide efficient plant status assessment with fewer personnel, like in nuclear plants. I mentioned spread spectrum. And we are on the Interface Standards Committee, so we're helping shape what that looks like. And we have to work in data flow architectures, so we have some computer science and double E's working in that area. And we put some of this, by the way, on the smart ship concept that the Navy is working on. It's called Reduced Ship Manpower by Virtual Presence, so that they're able to reduce the number of people who have to go around with clipboards making measurements of temperature and humidity and various other parameters in all the compartments of the ship. We can just do them with these integrated circuits and send the information wirelessly. Yes?
Do you work with any other companies on that, or is that something you do yourself?
Well, as a matter of fact, on the RSVP, we were working with the Intelligence Systems Lab at MIT and a couple of other industries. Industrial companies. I've forgotten who they are right now. But we have a lot of cooperative research and development agreements with private industries in this area, in this general area, and some of them don't really like it if we go out and tell everybody who they are. So because of the intellectual property. But yes, this is a very hot area, and there are a lot of private industries working with us in that area. And I think that'll just continue to grow. Well, we found, trying to work with atomic force microscopes, that they have a little fiber that actually reads the atomic force, that these fibers were very sensitive to humidity and temperature. So some guy came up with the idea of using that as a sensor. So what we've been doing at the lab is making little fibers or beams, and then you put a coating on that beam, a selective coating, so let's say it's sensitive to mercury. And then if there's mercury vapor, it will cause the beam to bend because of different sensitivities, get expansion, and some coatings get expansion, others contract in the presence of these things they react with, and so that gives you a sensitivity to these vapors. Similarly, you can excite this and get a difference in the vibrational frequency response. So there are a couple of ways you can use these little fibers to measure chemicals. So you could imagine something the size of your finger with 10,000 fibers on it, each of which has a selective coating for a particular chemical, so you could do a lot of measurements at one time. Well, we don't have that yet. We're just trying to do one or two right now. So, as a matter of fact, we have several patents issued and pending and a dozen disclosures on that technology. I've talked about customized coatings and arrays. This shows an example of the readout electronics and how you go to these little things that I call fibers, but here are shown as rectangles. And this is the original atomic force microscope optically read beams. So that kind of shows the similarity where we got the idea. Okay, another thing we're doing in the electronics area, out at the laboratory we were studying the genetic effects of radiation on mice because the mice genome is very similar to the human genome. And so for decades we have studied colonies of mice that we have grown and very carefully characterized so that we know a lot about their genetics. And so what we would do is expose those mice to various carcinogens or other things like radiation and then look at their generational abnormalities if there were some. Well, the problem is that you got all these hundreds of thousands of mice, you've got to have researchers to pick them up and look at them, and you decide, well, is that mouse okay or is that not okay? So we came up with a way of putting them on a little slide, putting them into an X-ray machine that circles the mouse, and then using our image processing guys, we can do tomography of the mice and look for skeletal abnormalities pretty easily. And then doing single photon emission tomography, which is you put radionuclides into the mouse, and these radionuclides might accumulate at the heart or the lung or the liver. You can get displays of individual organs to look for abnormalities there. So the couple of guys doing that have formed a company, Mike Paulus of our lab, and somebody, I don't know if they're from the university or not, but a lot of our researchers are spawning off little companies. So now I'm going to talk about our section, my section, the measurement science section. So I talked about electronics, now I'm going into measurement science. Well, for many decades, like 4 or 5, we've designed the control and protection systems of many research reactors all around the world, including either the South Pole or the North Pole, I think it's the South Pole, and also some reactors in space. So we've got a long history of design and analysis for instrumentation and control for research reactors and space power reactors. We've also worked on the control and safety issues for light water reactors, liquid metal reactors, gas-cooled reactors, and then other commercial power plants. We still have some ongoing research in these areas, especially for gas-cooled reactors and light water reactors. And this is an area where there's opportunity for collaboration that I'll get to right after this slide. Now, if you remember the organization chart that I showed you, and I said I was going to come back to that, if you can kind of put that in part of your mind, think of an organization chart, What we have done is develop a supervisory control technique, and if you could think of Lee Dodds as head of the department, and he in some fashion, some loose fashion probably, controls the department, okay?
Very loose.
Okay, well, we simulated the data flow and the plant heat transfer and fluid flow and neutronic performance. And then we got a hierarchical distribution of controllers. You know, in the organization chart I showed you, there was a division director, some advisors, and then the section heads, and under them there are group leaders, and then there's staff. That's a hierarchical distribution of control. Well, what we have done is put rule of thumb control at the highest level of the hierarchy, which is counterintuitive and is different from what almost everybody else in the world has been doing except NIST. NIST also is doing this. Now, what that means is a lot of control theory used to be implemented in big computers with all the control algorithms and all the diagnostics running in that computer. And if the computer burped, the whole plant had to shut down. There have been several instances in nuclear power plants where things had to shut down because the main computer burped. So we decided that we would put a lot of the intelligence out where the control actuators were, and the sensors and the actuators, and then do a lot of the signal processing there and a lot of the control algorithm selection there. But up at the top, we would ask ourselves a question: are we in the right operating envelope or not? Are we in a safe environment or not? And if not, we shut down. We've used that in the nuclear enterprise ever since it started, actually. It's called a SCRAM system. If you'll think about that, that's a pretty dumb system. It just shuts you down if you violate some set point. And so this rule of thumb control, like, let's suppose that all the professors were gone and Lee was here to run this place by himself and some issue came up. Well, he might not handle the problem as efficiently as some of the professors, but he could keep the organization running. And so for a while. So what this kind of control does is keep the enterprise running for a while to give the human operators time to come back in and intervene. The other thing that we did is do look-ahead projections to determine when various things were going to happen, like valve actuation or motor actuation, when other trip points might be exceeded, and tell that to the human operator. Communication to the human operator about the goals of control actions and proximity to control boundaries. We learned about this from airplane pilots when automatic landing controls were put in jet planes. We found that the pilots always turned them off before they landed. And the reason was the stress would build up to such a high level because they weren't sure that the automatic control system was going to function correctly. They would turn it off and go into manual control. And we found that in nuclear power plants that was happening also. So what we've learned is to support the operator in various cognitive phases like hypothesis generation, hypothesis checking, monitoring, and rule-based operations. The kind of information the human operator needs varies depending upon his cognitive state. So we've developed that system, and what we would like to have is some enterprising students to take it to the next stages. Is that strong enough, Jen? Which brings me to the NERI program, the Nuclear Energy Research Initiative, which is funded by the DOE Nuclear Energy Office. It's a $60 million program in 2003, I think it is. This year it's like $30 million. It's growing rapidly. It's a good, truly open, competitive opportunity for 3-year research programs. And having sustained funding is something that's really important for researchers. Funding that doesn't just last for 9 months to a year, but is multi-year. That way it gives more opportunity for dissertations, in case any would ever take that long. We're strongly encouraged to assemble teams of university, national lab, private industry researchers. This is a very popular program in Congress because it is open competition. And if there's one thing that we like in America, it's open competition. We have teamed with NC State and you folks on a NERI project that develops automatic verification of plant requirements as a plant ages. Because requirements change as a plant ages, but sometimes people forget to go back and update the requirements. So what we're doing is guaranteeing the control system is meeting the requirements as they exist now, and if they don't, to switch over to another control algorithm strategy. That's a 3-year program. Belle, I think you're involved in that, and I don't know how many students you have involved. Okay. And this comes up every year. The call for this year is already passed, but about December, January of this coming December, January, there should be another call. And we'd certainly welcome the opportunity to team with you. Now, there's another program called Nuclear Energy Plan Optimization Program. This is primarily for improving existing reactor designs. The proposal calls are out now. They're due to DOE-NE on March the 30th. That's up to $375K per year. This year is for human factors guidance for digital I&C and hybrid control rooms, for development of technology for online monitoring of non-redundant sensors, and this is interesting, research and development to address nuclear power plant vulnerabilities arising from transmission grid voltage inadequacies. As we become more decentralized in our national power grid, there are more opportunities for upsets on the grid. And so somebody's asking the question, well, what might happen to nuclear power plants if you get rolling brownouts or you get some other upsets?
Is March 30th the deadline for pre-proposals or final details?
Final proposal. Right. Okay, now I'd like to go into another market, which is international security. John Mahauzo and some of the people who graduated from this department have developed a leading capability in the world to monitor fissile material in various configurations. This is an unclassified slide showing that we can put a californium source, californium-252 source, on one side of some fissile material, whatever it might be, and then get a series of detectors on the other side, and then monitor the radiation that gets to the detectors. Now, I've shown here what this looks like in air for that configuration. That's no fissile material at all between the source and the detector. What you get is transmitted gammas. This is the center line of the gamma peak, and those come almost immediately. Oh, I need to back up and show you something else. What John did that was very innovative and nobody else has done that I know of is this source is really in an ionization chamber. And every time you get a fission, some of the neutrons will go in the ionization chamber itself and create a signal. Other neutrons will go through whatever you're interrogating. So doing very, very refined timing and coincidence counting, you can determine the relative incidences of these neutrons and gammas at the detectors correlated to the fission. So this shows like 1 times 10 to the minus 9, 10 to the minus 8, 10 to the minus 7, 10 to the minus 6 counts per source count, and there are about 1 million counts per second in the source, so that would be like 1 per second. So what John has done is help get the electronics developed and the noise analysis and stochastic processing developed to be able to determine by the shapes here, so this is an air, and this is when you have fissile material, and these are neutrons that come from fission induced in the fissile material. He's been able to determine
Horizontal scale.
the horizontal scale is in nanoseconds. I'm sorry. The electronics that John used to do this 5 years ago filled up a trailer, as in tractor trailer. Now it can be done in a couple of briefcases. And the reason we've been able to do that is because of high energy physics work, reducing the footprint of the electronics and the capability. Because of that, we've been able to finally make this a portable system. As you can see from this other slide, that's a pretty small, well, you don't see the electronics processing, but it's about the size of a briefcase. So John has gone all over the world to do this, and right now several Russian facilities have this system, and they're wanting to use that in their future systems where they are dismantling nuclear warheads and storing material to verify that material is what they say it is and remains in place. So he's having a lot of effect on to start 3D. Another thing we've done is, speaking of dismantlement of warheads, this country is paying $12 billion for the Russians to dismantle a bunch of nuclear weapons and get out 500 metric tons of highly enriched uranium and blend that down to reactor-grade material. And this blending down is taking place in gaseous diffusion plants in Russia. And one of the questions that our Department of State had was, how do we know that what is coming out of the product line, this is a blending tea, this is highly enriched uranium, this is low enriched uranium, this is like 95%, and this is what, 0.3, whatever natural uranium is, 0.7? Okay, and what we want for nuclear power plants is like 4%, something like that. Well, how do we know what the Russians are selling us actually came from this and isn't just coming in this line? Okay, so what we have done is develop a system using Californian sources again to irradiate part of this high enriched uranium pipe, and we do it by putting a shield in place and taking it out at a certain frequency. So we have a periodic signal of fissions that we're generating. So, you know, the periodic pulse of neutrons are hitting the pipe, and so as the material flows down the pipe, we look for that time-varying decay of the fission neutrons, and then we trace that through this pipe. So we have this kind of system in this pipe and that pipe, and we do correlations to verify that what we're getting here, that we look for the same time-varying signal here that we have up there. This is a system that Los Alamos built that measures enrichment. So this is a very popular system with the government. We have it installed right now at Novorusk, where Jose Marsluga tells me, first time he went there was 7 inches of ice on the road, and that was on the road. And he goes over for several weeks at a time into this gaseous diffusion plant called Urals. EIP stands for something like gaseous enrichment something or other plant. So we've got that in there. It's been in there a couple of years, working very well. We're planning to put another one in at Zelenogorsk, which is another gaseous diffusion plant, and then we have plans to put it in a third plant. The Californian sources are coming from Chelyabinsk 70. So that's a very popular system, and the Department of State says that we have monitored the equivalent of the dismantlement of 4,000 nuclear warheads with that system. Okay, so that's the Advanced Nuclear Measurements group that I was talking about. We do lots of nuclear things, but in the interest of time, I better go on and talk about some of the other areas that we have. In radiation detectors, we do development, testing, and evaluation. One thing that we're beginning to do is go back and look at solid-state materials. Several years ago, there was a lot of research looking for anything that we could think of that we could make into a neutron detector. Because of the improvements in electronics and better understanding of materials that we've gotten at the laboratory, we're going back, taking a new look at various things, including solid state, to see if we can't make high-quality, room temperature neutron detectors. We're also beginning to get into biotechnology sensors, and I have some slides on this later. A particular thrust of ours that we would like some help from you, if you can, is in the area of nanodosimetry. As you know, there's some controversy about how much radiation is bad for you, and there's some competing theories about whether or not a cell that gets damaged by radiation communicates somehow to another cell, a neighboring cell, to kill itself, so that there won't be some propagation of damage throughout the organism. At least there are two big theories I know of about how cells get damaged and organisms get damaged by radiation. But what we don't have is any good measurement of what's going on inside the cell whenever the radiation hits it. And that's what we're after. We're building nanodetectors, and we need some help in nanodosimetry modeling. Anybody that you know of, or any of you who would like to help build capability and a career in nanodosimetry, I'd like you to call me. We also are trying to make physical measurements in harsh environments like steel plants, glass smelters, for example, and then control of nano and microsystems. The ability to interface to the cellular world, we think, is going to be an integral aspect of basic research and applied technology. We have here a cell that's being pulled up into a capillary, and then we have some probes, and these probes are monitoring electrical activity in this area, which is being affected by what's happening to that part of the cell pulled up into that capillary. Here's another a very faint picture, because it's very small, of another electrode impinging on a cell. This is a diagram of what that looks like. Still another attempt to measure what's going on inside the cell. This is a slide of some work that we've done in building bioluminescent bioreporters, and which means, we call it critters on a chip. We've taken luciferase, which is what lightning bugs use to make a flash, and we put that on a chip along with some compound that I can't remember that interacts with contaminants, and we put this in a monitoring well, and then we get one of those wireless transmitter chips I told you about. So when a contaminant, like in the groundwater, comes along and interacts with this biological material, it will flash, and then the light will be transmitted picked up by the chip, and then a signal sent up to the receiving center at the top of the well, so we can monitor the flow of contaminants in groundwater. But we'd also like to do this in biological organisms if we can. Over here, we're interested in molecular electronics. What we've been able to do by monitoring or designing how messenger RNA in genomes and various aspects of the insides of cells, how they are activated by various conditions. We've been able to build OR and OR gates, and so we think we see a way to transcriptional logic, which could lead to some advanced computing. There's a lot of research in that area going on around the world, not just in our place. Well, I told you we work with the semiconductor industry, and that was important for us. You can take semiconductor processing capabilities and put some things together. Now this is not regular like this. This is just something we play around with in the lab. That's a Chinese hamster ovary cell. But you can grasp very quickly that if you could address each one of these little things, these little probes, and if they were to penetrate this cell, you could pretty easily measure what's happening inside the cell in terms of electrical activity or electrolyte activity. So this is another example of where we have gotten this hamster ovary cell and impinged it on one forest of these features, and it's broken off. You can see how some of them have broken off and stuck in there. So this is work hot off the press. It's something that we think is going to be very important, and the reason it's very important is we want to be able to monitor in the cell in real time how the cell is reacting to various kinds of irritants or threats. Okay, I'd like to switch now to our Advanced Lasers and Optical Technologies group. What these group guys have been able to do is build, using heterodyning approach, lasers that can look out in the distance, like at this. For example, this is where an airplane has flown by and there has been smoke. The airplane has flown through a smoke screen, and this is turbulence off the wing, one of the wings of the airplane. And turbulence is important if you're trying to jump out of the plane with a parachute. Okay, so the Air Force is pretty interested in measuring turbulence. What we can do with a camera is measure that turbulence directly. And I don't have time to go into all that, but that's pretty exciting research. Another thing that we've done is build a direct-to-digital holographic capture and display system. We're making holograms without plates or films. We're doing it directly, so you can view it on a CRT. And this is an example of something we did a few years ago. Right now, we're able to look in these very complicated semiconductor chips, and right now we're seeing 70-nanometer defects. We'd like to get down better than that, but we're already smaller than the wavelength of some of the light we're using. A quarter wavelength of light is about what we've been able to do so far. and that's only with advanced image processing. So that's pretty interesting stuff. What I find even more interesting is sub-wavelength structures. You know, if you have a grating and you hit the grating with some sort of wave, you get some diffraction or refraction pattern out of that. And as you change the dimensions, you can get a wider angle of the waves that come out. It turns out that when you get sub-wavelength, you can get the light to bounce around in there and re-emerge. Okay, so as you can get these features smaller than the wavelength of light, you can get some very interesting properties. As a matter of fact, what we've been able to do is put together some designs where if this is the percent reflectance and this is wavelength, that's 10.4, 10.5, 10.6, 10.7, 10.8. You see at about 10.56, we've got a very sharp reflectance peak, which would mean that if you were shining a laser on something, you can get that particular wavelength or band of wavelengths reflected, and the others wouldn't be reflected. It leads to some very interesting possibilities that we can't talk about here, but I'm sure you can imagine. One thing that we can talk about is we've come up with something called smart dirt. Let's say you've got some of these sub-wavelength structures that are designed to reflect a certain wavelength. And by the way, that last wavelength coincides with one of the major wavelengths of an CO2 laser. Okay, so we can design these little puppies so that they reflect CO2 laser beams at distances up to about a mile and a half, and these things are the size of dust particles. So what I could do is throw some dust on Lee and let him get about a mile away, and I could identify him in the crowd by hitting him with a laser at a certain frequency, that one frequency I showed you. If I get a reflection back, it's more than likely going to be him. Or I could throw it down on the ground and let him walk through, and then I could look at his shoes. So that's some pretty interesting stuff. But we've also found, that we can take these features and turn them into the equivalent of electrical circuits. Sorry, I don't have time to go into that. But we can now make integrated electro-optic devices that have a lot of promise for communication at very high speeds, and we're using those now we're planning to use those on chips at some of the research we have to do optical interconnects. One of the things that's slowing down the migration of chips in terms of power is the ability to do interconnects from one thing to the other. And we're trying to see if we can't have a lot higher bandwidth using optical technologies, and we think we can using these sub-wavelength structures. So, integration of silicon and biology is something that we're doing at the lab. Here's the B chip, and this is the luciferase that I've talked to you about. Now, all these things are possible because of our other section called Signal Information and Knowledge Processing. Remember I told you that on the USS Hayes, we have put the world's largest computing resource 5 or 6 years ago, and we hang all these hydrophones in the Bahamas. We send submarines through and characterize the emanations. To do that resulted in several PhD dissertations and several master's theses because we had to do something called beamforming, which has to do with how you interrogate these hydrophones, and Bell probably knows a lot more about that than I do. If you have any tough questions, he can answer. That's been a long program, and the time scale doesn't show up here, but it does on my slide if I squint at it. This says we started in 1985, and we're still working on it, and spent about a $45 million program so far. Now, I only talk about this to tell you that it's a capability that did not exist in the world. It was important to national defense, and it's resulted in a lot of work for a lot of people for a long time, and it's been very interesting. Something that I find even more interesting is called the Enclosed Space Detection System. This is a system based on novel wavelet-based algorithms that, because of the ballistic nature of your heartbeat, which vibrates your body every time your heart beats, and you vibrate whatever you're in or on. If that is something with a suspension like a big truck or a car, we can monitor the vibration of the surface, either contact or non-contact, and determine whether or not there's a person in the car. Now this has already been licensed, is in place in a few prisons. There's a prison in Nashville where they caught a couple of years ago a prisoner hiding in a laundry truck. And the way they did it was they just put the sensor up on the truck after the engine was shut off, and you wait a couple of minutes for things to calm down, the gasoline sloshing back and forth, and then the prisoner's heartbeat vibrated the truck enough we were able to pick it up. And that gives you an idea of the level of capability of signal processing that we have. And if we have it, you should assume that other people have it too. I thought that was pretty cool. Image science, sorry? Not for the prisoner. Yeah, he was surprised. Image science and machine vision. This group is headed up by an ex-nuclear engineer from University of Virginia, Ken Tobin, and his work helps us image these mice and helps us image the semiconductors that I was telling about. Also helps do digital fingerprint digitization of fingerprints. He's also involved in video forensics. We were involved in a case in Chattanooga where somebody walked into a convenience store and shot the owner, and we were able. And the videotapes of these convenience stores are pretty awful because they just run it and seem to never clean the heads. But with his image processing capability, he was able to get good enough images that the suspect admitted guilt. But they've got 10 researchers, 4 PhDs, 5 MS, 1 BS, and a budget of that, and this shows the kinds of things they do: image scene analysis, pattern recognition, color processing, systems integration. And these are examples of what he does that I'm not going to go through because of the time, but they'll be in the archives for you to look at, or you could come up after this and talk about it. So I'd like to talk about some highlights and then strategic areas, and then I'll be through in just a few minutes, 3 or 4 minutes. So in calendar year 00, our highlights were in science at Brookhaven's relativistic heavy ion collider. We put in 450,000 channels of detector systems electronics. In industry, we had successful completion of a cooperative research and development agreement on our direct digital lithography technology that resulted in an $18 million NIST, National Institute of Science and Technology, ATP, Advanced Technology Program win. In national security, we provided technical support to the high-enriched uranium to low-enriched uranium blend-down project over 3 years, dismantling the equivalent of 4,000 nuclear devices. And strategically, what do we want to do? And this is where we need, where we're looking for collaboration in the next few slides. In energy and in the environment, we want to look at distributed energy resources as we become more decentralized in this country, and how we put communication, information, and control infrastructures in place to support that. The distributed wireless sensor systems for industries. We want to get more penetration in that market, and we need collaboration. There's more work than one organization can do. As you know, we're building a spallation neutron source in Oak Ridge. We are developing the next generation of neutron detection, imaging, and readout technology right now. Some of the SNS people are working hand in hand with us on that area. Then EPIX is a software package built to control accelerators, and we're building control algorithms for SNS. In the physical and computational sciences, we're going to develop detector system electronics for ELISE, which is a collider at CERN in Europe, and ORNL, which is a neutrino detector system or system that's going to go in SNS. We're looking at entangled photons, and how we might use that for nano-resolution surface profiling. And then we want to support the next generation of computing platforms. In biological and environmental sciences, embedded wireless microsensors for medical applications, development of intracellular probes for molecular activity, and then we're looking at development of massively parallel computing at diagnostic structures based upon cellular systems, biological computers. In the national security area, there's a gas centrifuge program that may be coming back because Congress is getting worried about the supply of reactor-grade uranium and relying on the Russians for the supply. They're a little nervous about that, so they think we may have to bring back the gas centrifuge program. Developing the next generation nuclear weapon identification system for Start 3 verification, and developing the next generation seeker technology for the future combat system and for the ballistic missile defense organization. In terms of new emerging technologies, I think you heard from my presentation, be nanotechnology, nanoscience, and nanoengineering, advanced prognostics and health assessment. I haven't talked much about that. Molecular electronics, micro-miniature electro-optical systems, and quantum systems. We are in a hiring mode. We need a nuclear engineer for experimental and simulation work at the PhD level. We need a nuclear engineer with experience in nanodosimetry, or a health physicist, I don't know if they're the same thing now or not. We need double E's in single-dimensional signal processing and stochastic signal processing. I know this department at one time, and probably still is very strong in that area. Image processing engineers, RF and microwave engineers, and analog to digital designers. And with that, I'm done. Thank you very much for your time.
Okay. May I have time for a few questions or comments? Okay, Andrew.
You said that I&C was working on neutron detectors.
Yes.
Can you tell us more about that?
Yes.
Work and what they're targeted towards?
All right. There are two types of detectors. One, I remember from the Phoenix experiment where I showed that there was going to be a place where you get particles going off in all directions. And in neutron scattering experiments, you have neutrons going off in all directions as it do Bragg angle scattering. You'd like to be able to have wide area coverage at low cost. And right now, using BF3 tubes is what they use. You don't get very high resolution. They're expensive. They're not really very satisfactory. We're trying to make solid-state detectors, so we get lots better 2D imaging. In case that doesn't work, we have another 2D neutron imaging detector, which is based on neutron phosphors, and using wavelength multiplexing, so you have a grid of these fiber optics, all of which can fluoresce if neutrons interact with them. And because using electronics, you can determine where the interaction took place by timing the difference in when the signal gets to each end of the optical cable. So we're using those. Also, there are beam monitors, measuring where is the beam. These are intense beams, and the beam isn't always exactly where you want it. So you have to measure where is the beam actually in real time. So that's what we're doing. And we're looking at various kinds of new materials. They're not really new. They're materials that were looked at in past years and were kind of judged as not being adequate. But now because of superior signal processing, we think they might be adequate.
Is one section more is stronger in dynamics than other sections?
Yes, right now the electronic systems section is stronger because they're integrating the biological and physical material on chips, and the other sections are catching up, but they're the leaders right now.
Andrew? You said that you were working on micro cantilevers. What are you doing there? I know the inventor is actually Dr. Thundat in the LSD division.
Right.
But I know that Chuck Britton was working on the electronics.
That's right. We do the electronics. That's right. He does the materials work and some of the physics. He does the materials work and some of the physics. We do the electronics. And that's done primarily in the electronic system section.
where is that going? I remember that I saw a chip that was made that had the electronics on board a few years back, I guess. Are you all developing improved control electronics or what?
We are, well, you know, they're trying to go from one or two detectors to an array of detectors. Whether they've been hung up for some time getting materials to stick to the cantilevers just the way they want them.
Yeah.
So there's been materials problems. We electronicers think we can do our part. Seriously, I think that they've kind of gone through a slowdown period as they try to get better materials to stick to the cantilevers.
Yeah.
And then once they do that, then there will be more need for us to do these fingers. You know, how if you had all these, like a little porcupine with all these sensors on it, how do you address each of those electronically and control them?
Are you all sticking with the capacitance method of function detection?
Right now, I think we are. And optical techniques are possible, but right now, I think it's capacitance.
Any other questions or comments?
I might add that the hiring mode that you described, we can supply graduates in all those areas.
Good.
We do have a health physics program in this department, and a lot of our nuclear engineering students can do a lot of those double E activities that you mentioned, and we can help you with all of them. Any other questions or comments? Let me say that this is really exciting stuff going on here. One time, about 35 years ago, I was a member of this division, and that's where I did my PhD dissertation. And it's much more exciting now than it was 35 years ago. So thank you for coming and giving an outstanding feedback. We do have refreshments down on the second floor, and everybody's invited.